would talk a bit about form and distinction. I try to talk about this somehow from the beginning. So what we're thinking about here is the notion of a distinction. And I have to explain the method. The method is by experiment. That is, I wish to look at some things that we would call distinctions. And I want to think about what happens when a distinction is made. That's one part of it. Another part of it has to do with a particular way of proceeding, which is that there is a notion that meaning arises in relation to, can't spell relation, in relation to form or syntax, if you like. So that if we had no language to begin with and there was only an emptiness, then I would grant you that there has to be meaning even there. And while what I'm doing may look a little like formalism in the sense of Hilbert, it's not, because of the following key point, which is the repetition of this point, that there does not exist an uninterpreted formality. What constitutes an interpretation, of course, is another matter. How do you interpret emptiness? How do you interpret a form? How do you interpret anything? But it gets interpreted at the very least in terms of itself. I make a gesture of some sort, and this gesture has some meaning for you. Maybe more meaning as you look at it, maybe less. But it isn't uninterpreted. It isn't just some pure game or counter in a game. It is what it is. And you may turn it into a counter in a game. You may turn it into a piece of mathematics. You may turn it into a something which is making a distinction between an inside and an outside and ignore that it looks somewhat like a whale. You may do all kinds of things with it. There are all sorts of meanings available. We narrow it down by taking certain rules on, but we are thrown into language to begin with, language and forms. We're thrown into language and forms, and we do them as we do them. And we are not restricted to speak logically. We are not restricted to speak correctly or politically or any such thing, not at the beginning. But of course, we live in contexts, and in those contexts, the way I speak may be very important to you. And the way I draw things may be very important to you. And you may wish to follow my reasoning, or you may not want to see any reasoning. There are all kinds of things. So how do we begin? By talking about distinction. What would constitute a distinction is something which for you appears to be distinct. Something becomes distinct from something else, from a nothing. from a nothing, that is to say, from a situation in which the distinction didn't happen. And that there has to be with it, it is accompanied by an awareness. And I have no definition for awareness, but then I have no definition for distinction either. But that the distinction is not something that just exists by itself. So for example, this distinction here is no distinction if there's no one there to look at it. It's only in the course of your looking at it that it becomes a distinction. The tree may make a noise as it falls in the forest, but this entity here makes no distinction unless there's someone present to examine it. And of course, you can argue with me about that, just like you might have argued with me about the tree, in that you can say, well, we'll set some instrumentation to determining whether we are inside or outside. And we could even set mathematical instrumentation to determine whether we're inside or outside, such as drawing a straight line until we went into the unbounded region and finding that we had crossed the boundary an odd number of times, and that discriminator tells me that I am inside rather than outside. So I want to share with you the kind of language that Spencer Brown did create. Let me see, let's call this F1. And we'll leave it in documents, okay. The kind of language that Spencer Brown created to attempt to do this kind of an experiment of taking a person into very, very simple language and allowing these thoughts to evolve as they might. Excuse me, I'm just making sure I'm getting a slide to happen. There. Okay. So he said, in language, he said, we take as given the idea of distinction and the idea of indication. And that one can not make an indication without drawing a distinction. We take, therefore, the form of distinction for the form. The subject here was not actually distinction. The subject was form, right? But what is form, and how would you get to that? And you begin with the experimental, and in this way of speaking, there is the notion of indication, which allows the possibility of another, or yourself with regard to it, and it's at the level of an idea. But if you make an indication, you certainly draw a distinction. That part's logical. And then the next part is highly self-referential. We take, therefore, the form of distinction for the form. So that if I asked you, what is the form of this? It's the form of the distinction that it makes for you or for me. That's in the ideational part. And then you go back to experimenting and you realize that all of the words that you have made are all indicators of some distinction, and they all are falling together into just something being made distinct. And I'm jumping the gun all the way over to the notion that you had best draw one. And start experimenting. And of course, the kind of experimenting that I'm going to do here is different from what we might do in a room, because if we started here, we might leave the lecture entirely and draw a distinction by rearranging the chairs in the room and looking at the consequences of that, or some other distinction that we could make and watch the consequences of it and begin to understand what's involved in the emergence of a form, not from nothing precisely, but from no form that there was before that. But if I'm going to do this on a sheet of paper, then I may make a distinction in the sense of drawing a curve in the plane which distinguishes an inside from an outside. And it's something that we can agree upon. And as you know, he decided to choose a particularly nice, simple right angle bracket to indicate a distinction. So this itself stands for, or corresponds to, a distinction which I'm going to draw by filling it in. So this distinction is a distinction in this box between an inside and an outside. Perfectly fine, very definite distinction. Unless you were to start to ask about what does it mean to be in the boundary, and are you on one side or on the other, as with any distinction. But this is still making a distinction. So at this point, something symbolic or signifying has happened, because this is a sign for a distinction. I'll just write this. It also is a distinction. So at the point when this occurs, and it doesn't actually occur here so easily because you don't think of this as a sign, but here you think of this as a sign, and it becomes a sign for itself. So this guy here is a sign for itself. It's a sign that represents itself. And I keep repeating myself because what's happened is unusual. Something funny with my, now that worked. Yeah, okay. Right. What's unusual here is that this point, it gets easily missed. That if you started from very little and you made something which could be regarded as a distinction, but it could also be regarded as a sign for distinction, and in fact, a sign for the very distinction that it makes, then sign and object have coalesced. Sign and object do coalesce in our cognition and in our way of being aware, but when you go searching for self-reference and you go searching in reference and you go searching outward into how do human beings become signs for themselves, for example, which is C.S. Peirce's philosophical quest. For C.S. Peirce, the sign for itself was the ever-expanding collection of signs and symbols and forms that a human being becomes layered with until it begins to stabilize at near infinity, and so emerges the human being in some distorted way that I have spoken of here. But the sign for itself occurs at once from the beginning, if you take the beginning slowly enough to watch it happen. And so that's what happens semiotically before any mathematics has occurred in this situation. And there's enough happening semiotically here that you could continue with this at the semiotic level and never touch any mathematics at all, if you wanted to. So how does mathematics get started? Well, I think in this instance, and I wouldn't try to make a general principle out of it, but here, the mathematics, the fact that it starts to become mathematics, is starting with a use of an equal sign. So this harks back to Nick's story about avoiding the literal use of the equal sign in category. But in this kind of symbolic mathematics, it's the use of an equal sign. It's the saying that a something is equal to something else. And so, for example, I may write, following this symbolism that we're playing with, I may write this. I may write that this can be set equal to this because this is a form and this is its name. And it doesn't need its name tag. And so we can set them equal to one another. We can write 2 marks next to one another is equal to a mark. And now we have started mathematics. Now mathematics has begun in the sense that there is a notion of many different forms which all represent the same form. And there is a notion of calculation as well, even without setting up anything else. I have some modulo 2 mathematics, right? If I had given you now this, and I said, what is this equal to? Or you would take the pairs and you would allow them to condense and you would say, well, it's equal to this. But then there's another pair and that's equal to this. And then there's another pair and that's equal to this. And then you would have realized that you had arrived at a big theorem, which is that if you had any big row of these whatsoever, finite row, and the notion of finite versus infinite has arrived here as well, will be equal to just a mark, right? And we've now done mathematics. Suddenly we did mathematics out of semiotics, out of the consideration of a self-referential symbol, out of the consideration of form, out of the consideration of nothing, out of the consideration of the possibility of there being a distinction. But suddenly we did mathematics because we had the notion of an equality, the notion of 2 things being equal. And we could make theorems like this wonderful theorem here, that any row of marks is equal to only 1 mark. Of course, this is not exactly the most exciting mathematics you ever saw, but it's mathematics, all right? And furthermore, coming out of that, because of the actions of making multiplicities, the actions, I haven't formalized them, right? But the actions of making things give rise to the notion of finite, because You might well think, well, what if it didn't end? What if it didn't end? Um, what would it mean not to end? I don't know, but what if it was so very, 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 very long? Well, then can we still say that it's equal to a mark? Um, it would take you longer and longer and longer to reduce it. If it were sufficiently long, it would be beyond your lifetime to reduce it to a single mark using only, you're only allowed the simple tool of 2 marks next to one another condensed to a mark. So, so we would be out of luck. It wouldn't reduce to a mark. But then that other idealized infinity.
Lou,
Yes.
I have a quick question before you go on. Sorry to interrupt. Does that depend on reducing 2 marks, reducing to 1? Does that depend on the parity, even or oddness? Or is it always just going to reduce to 1 mark, whether it's even or odd?
Where you introduced a concept that hadn't occurred to the person who was using this yet. Well, all we know is that 2 marks reduce to 1, but it doesn't depend on the parity, does it? Because 3 marks equals 2 marks equals a mark.
1 mark.
So this mathematics is extremely simple mathematics. It's just that a row of marks will reduce to a mark. But there's the idea of idealized infinity. Idealized infinity is the notion that you could have a row of marks that goes on forever, going on forever. Where did we get that? Well, I mean, we can see where we got it in terms of our experience. Our experience was not forever, but very large, so large that we couldn't handle it. We couldn't handle the reductions, in fact, right? But the idea of forever, if I called it omega, this infinite row of marks, I have it continuing on to the right. It's like the hallway in Hilbert's Hotel, where this is room number 1 and room number 2 is to the next of it, and there's an infinitely long hallway and it goes on forever. You imagine it. We have this idea. We can see where we got this idea, but the idea itself wasn't exactly in our experiences of writing things down on paper. It had to do with the fact that we make a distinction between all of that activity that we do and jumping out and looking at that activity and discussing it. It couldn't have arisen any other way, that notion of infinity. But we ended up re-entering it. We ended up re-entering it back into the symbolism, right? We're all familiar with how we might do that. We might say, well, this goes on forever. And this itself is omega right there. It's no different from this omega. It's a row of marks that goes on forever beyond our ability to count. So it could be huge and finite and still have this property for our perception, or it could be truly infinite, whatever that would mean. But whatever happens, we've now found a symbolism for it, that the omega is the same as a mark next to omega. And this is a new level of self-reference. In that omega refers not to itself, but to a part of itself. What we say about omega is that omega actually is referent to and identical with a part of itself. And we arrived at it because we became very good at cutting marks in a stick, and eventually thought at some point, as some person did long, long ago, what if I made as many, more marks than I could ever make? What if I had a stick on which there were infinitely many marks? What if? And this action of us, that we can do this, is part and parcel of a part and parcel of our ability to make distinctions. I'm not sure you could have made the original distinctions without that same capacity, but it becomes very hard to talk about. It's easy to do. It's easy to begin to think about infinity. Some people object to completed infinity and would only want to talk about a very long row. But even if I had a very long row, I could still say of a very long row, I could make a very, 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 very long row. Like this one. It's very, very, very long, and I'll call it omega. I'll call it omega, omega 0, okay? And then I have here this guy here, and this is an omega 1. It's a different omega, but you would have to do some work to see that it was different, right? You would have to learn to count. And then you have omega naught is equal to a mark next to omega 1. And if you're talking finite things, then you would say omega 1, omega naught. It should be omega 1 and omega naught, shouldn't it? Omega 1 has one more mark than omega naught. Right? One more mark. But if it's infinite, then they're the same. And we tell tales. We tell tales in order to examine these infinities. We tell tales like Hilbert's Hotel. And we have invented, along with all of this, we have invented names for each of these, right? Somewhere along the line, we invented names. 1, 2, 3, and so on. And we have that infinity. And mathematics has started, even without the other law that comes from laws of form, which is important, and I'll mention it. Well, the point that I wanted to make is that you start by, if you start by saying, I just want to examine language, I just want to examine sign and symbol and semiotic, as soon as you walk into that natural human tendency of saying, well, I think I will have this is the same as this, you start doing mathematics. It's inevitable. It isn't that it was out there in some external world or in there in some internal world, but it's part of the activity and it somehow can't be avoided. But let's continue with the rest of that story, because it's very interesting what happens with the rest of that story. The rest of that story, we have 2 principles that came out of this. The other one was this one. And how was this rationalized, that this is equal to nothing? One reads this as a mark over A corresponds to crossing from the state A. And this is Spencer Brown's invention, actually, but we could think of it as elevated to a principle in a moment. That is to say, you have a distinction, and you have the notion that you are in one part of the distinction, and you cross, and cross is denoted by the same symbol into the other part of the distinction. So if this is the unmarked place, then you cross into the marked place. Or if you were to cross again, you would cross from the marked place and you would end up in the unmarked place. And then, having adopted that the symbol shall denote the crossing, you have that if you started in the unmarked place and you crossed and then you crossed again, you would end up in the unmarked place. But the unmarked place isn't marked, and you end up with crossing twice gives you nothing. But what happened here is that now the mark means name, even its own name. And it also means action, to cross. And you may object at this point. You may say, well, I didn't want it to mean two things. I want my symbols to mean only one thing. But on the other hand, it's perfectly compatible with the previous usage, because I can write this, which is almost mathematics now. You can't argue with it, but I'm going to assign different meanings to the left and to the right. On the left, it says you will cross from the unmarked state. On the right, it's the name of the marked state. And they're identical. The name of the marked state, where you arrived when you crossed from the unmarked state, and the result of crossing from the unmarked state. So it tells you that this sign can be regarded in the active mode or in the passive mode. It can be regarded as a sign for itself, or a sign for the marked state, or as a sign for the action of crossing from whatever is on its inside. And so all that fits together. And I couldn't say which comes first, the name or the action, the chicken or the egg in this case. But they are there together. And at this point, we've arrived at the full semiotics of the situation and the beginnings of the mathematics. So what do we have? What do we have? We have, if I put it back into words, that a form adjacent, pardon my spelling, to itself can be replaced by one form, a form taking itself as its own argument vanishes. So that's where we are now. A form can take itself as its own argument. A form can act on itself. And taking itself as its own argument, it can fit perfectly to itself and disappear. And those are the beginnings of laws of form, if you like. And this can be regarded as the basis, the semiotic or symbolic or self-referential basis that's worth contemplating. You can think of how does that relate to the way I handle my own form, my own notion of self. Or you can ask, how does it relate to the way I am collapsing or fitting together the apparently many different forms in the world of my perception or in the world of my thought. Or you can begin to do mathematics with it. And again, it leads to mathematics. And the mathematics is what emanates from being equal, right? And I'm not sure how far you can go with that idea. It's something to think about. That mathematics is what happens when you start playing with the equal sign. You can make a case for it, I think. What happens here, of course, is at the very simple level is that you can have more complicated forms and arguments, and they will simplify. Like, look at this one. Using only these rules, I get to apply crossing here, and then this will be equal to this. And now I get to apply crossing again, whereas it wasn't available to me here. And then I can do it one more time. And so this complex beast is equivalent to nothing, just like this one was. And another beast that I might draw, like this one, would be equivalent to something after a similar sequence of workings. So there is a mathematics of this, and more theorems that we could make, such as, what theorem would you have here? Well, that if I drew a concatenated form like this, it would reduce uniquely to either the marked state or the unmarked state, but you would need to prove it. There really is some mathematics happening here. And then on top of all that, which we'll jump across, you can get general results. And algebra. What you had before was arithmetic of a non-numerical nature like this, arithmetic of these, but then you get general results. What kind of general results? A next to a mark is always equal to a mark. A double crossed, whatever A was, will be equal to A. A next to A will be equal to A. More complex things like A next to B will be equal to A next to B without the B inside, and many, many more, infinitely many of these things. How do you understand them? You understand them the way you were told to understand algebra long ago, but maybe it's easy for us to forget what we were told to understand. We were told to understand that an equation in algebra means that it's always true in the arithmetic, no matter what numbers you put into the arithmetic. For example, n plus 1 squared is equal to n squared plus 2n plus 1. What does that mean? It means that one of the things that it means is that if you put any number in here and you square it, like 7 plus 1 squared is 8 squared is 64, it'll be the same as adding it up over here. 7 squared, 49, plus 14 is 53, is 63, and 1 is 64. That it works. It works for any number. So you can look at this and see that it will work for any number. If A was, there are only two numbers, marked state and unmarked state. So if you put in nothing on here, then you get mark equals mark. If you put in something, you get mark, but that's equal to mark, and so on down the line. So there are infinitely many of these. And the key thing is that we now have an operation. A goes to A cross. And this is very much like negation. And so the mathematics walks over and produces logic for you out of that. And I don't want to go doing a little course in logic either. The point is that what we've been looking at is how if you if you allowed that a form would, the form of a distinction would be the kind of form that it makes, and that a distinction is related to a form, that you then have all kinds of possibilities for looking at the way these forms would interrelate. And this system is a very simple one, but it leads to all those questions. And I want to dwell on what kind of things emanate from this before I show you something else. And we're watching the time, believe it or not. So what might I make of this? Well, one of the things I might make of it is going to infinity all over again like this. Only now I'm going to infinity inward in this form. And if I called that guy J, then this would be J is equal to J sitting inside itself. So instead of J next to itself, it's J inside itself. And we can play with that. And there are all sorts of these forms like this. But what I want to step back and look at before going somewhere else is just all the finite forms. There are a lot of them, right? I claim they can be ordered. Just like the ordinals in mathematics. And when you do piano arithmetic, which is what we started with, 1, 2, 3, and so on, you just have this very, very simple ordering. So I'm going to start with that, and I'm writing down all the finite forms. Mind you, I'm not collapsing them by the rules. I'm just writing them down, what they are, the 3, the 4, the 5, and so on. And now we got just the tiniest fragment of all the forms. What should we put next? Oh, how about this one? Right? These all have level 1. This is the first form of level 2. And then I can go back to doing this. And it goes on forever. Oops, sorry. So I'll have to jump to infinity again to get to the next stage. What shall that be? Well, it could be 2 of them. And then 1 more, and 1 more. And this is going to go on forever. And you see it's infinitely tedious or infinitely astonishing how many forms there are. You see, the only way to put them in a nice order, like a stack of cards, would be to take infinitely many of them, because they have a tendency to repeat in a pattern, and put them in a row, and then start another one, and start another one, and start another one. And you could probably understand that you're going to be able to order them all, but by what rule, and how is this related to what happened in mathematics itself? How is this related? In mathematics, how does this go? Are you familiar with it? Everyone should know about this. You start with 1 and 2 and 3, and you go on forever, and then you put in omega. And omega stands for like a row of infinitely many of these, if you like I did before. And then you have omega plus 1. And then you have omega plus 2. And then you have omega plus 3. But you think of these as numbers, as Cantor did. And eventually you get to omega plus omega, which is 2 omega. And then you get 2 omega plus 1. And you keep on going and eventually you get to 3 omega, and eventually you get to 4 omega, and eventually you get to omega squared. And then after a while, you get to things like omega squared plus omega plus 1, and so on and so on. And eventually you get to strange beasts like omega to the omega squared plus 1 plus omega to the 9th plus 3, and so on. And it goes on forever and ever and ever. And these are, this is just a fragment of the designators of infinity that Cantor invented, called the transfinite ordinals. But these all look like ordinary arithmetic expressions involving omega, ordinary algebraic expressions with lots of omegas in the exponents. And what I'm going to show you is that these can be matched exactly with these, so that the set of all finite forms in the sense of putting a form inside a form in these nested boxes and next to one another correspond precisely to the transfinite ordinals. And I'm going to show you that. By telling you a simple rule. That if I have a form A, then I'm going to let this will denote omega to the A. And this corresponds to 1. Oh, yes. And A next to B will correspond to adding. And now let's see how this works. Suppose that I took this one. So this is going to be equal to omega to this plus 1. Because whenever something is enclosed, it's omega. And then this is omega to the, oh, what about this one? Let's just get that one down. That's omega, you see. That's omega to the 1. Omega to the 1 is equal to omega. So the double cross is omega. So this is equal to omega to the omega plus 1 plus 1. Anything you write down can be translated. So it goes just like I said on the previous slide, 1, 2, and so on. And then you get to this, and that's omega. And then you get this, which is equal to omega plus 1. And so it goes. And now the curious thing is that we can now plug into the fact that we are used to this kind of algebra. So I could write some weird thing like omega to the omega squared plus omega plus omega plus omega. And I can translate it immediately into, oh my gosh, maybe I can translate it immediately. Over there on the right is an omega. This is up in the exponent, and it is omega squared. What's omega squared? Omega squared, that's omega squared. Omega squared plus omega. Omega to that. And next to an omega. You see? So we have a language, an algebraic language of a traditional kind invented by George Cantor for what all these are. And so they're finite. So it's a funny, almost a paradox. The finite forms of laws of form are the first fragment of the transfinite ordinals of Georg Cantor. And that means that the arithmetic that they form, in the larger sense of the arithmetic that they form, is much richer than the ordinary piano arithmetic. And one can play some mathematics with that. But I was just wanting to show you how, let's think back to what we did. We started with the notion of making a distinction and experimenting with how that would work and how signs arise and how our awareness of the signs arises as well, or becomes articulated, and we become aware of operations that we can do among them. And when we become aware of the operations and aware of the operations among the operations and of other signs that can be used, we start building an entire universe, and we find ourselves walking out into a mathematical universe, or even creating a mathematical universe out of very little. And what I haven't done is talked about physical world here. And I guess I'm not going to, but I do want to talk about other directions, because no one said we had to stick with these signs. No one said that. But what happens if you stay with something like these signs, like a distinction, and how it might interact with another distinction if it shared a bit of boundary with it? And you might say, well, if distinctions share boundary, we could allow that shared boundaries are erased. This is similar to the principle we had before of a form takes another form as its own argument, then they vanish. It's that principle in another context, but then this would become this, and that rather looks like the two circles becoming one circle. And this if they share this boundary, would become nothing. But on the other hand, a very heavily shared boundary, but not an entirely shared boundary, would lead to something different. It would lead to something like that. Or a partially shared boundary and a partially shared boundary moving along another boundary, that would give rise to other topological things. And you see, we're now in the realm of topological mathematics. And that was a slight shift of, and not such a slight shift, of including the boundary of the distinction into the discussion. If you include the boundary of the distinction into the discussion, you begin to look at things that feel like cell membranes, they feel like graphs and coloring, they feel like many things. And the kind of patterns that will evolve out of the mathematics that evolves are quite different from what could have happened otherwise. And then you can see that there is a kind of continuity between what we've been doing and all of the geometric or topological mathematics that you might ever think of. For example, a torus surface is obtained by taking somebody like this and attaching the upper edge to the lower edge and the right edge to the left edge. And of course, the edges vanish, but what happens when you attach? When you attach, you get a cylinder. And then when you attach here, you get a torus. And if we were thinking of the Mobius, then these would be distinct, but we would have an A here and we would have another A here and a little twist. And we would find ourselves with the Mobius band. And all of the different geometries of boundaries and interactions that occur at the level of a two-dimensional world, like that. And so all of these things are very closely related. The question is, how do the signs that should actually stand for the objects in question, they should be self-referential, but they also have to be perspicuous enough to not get in the way? How can they be used to study the kinds of things that one wants to study? So maybe one wants to study how things act on a surface and one represents the surface by something like this. Maybe one wants to study um, how some kind of knotting in three-dimensional space or in higher dimensional space, like with Sam today. How does something like this behave as it behaves in its own environment in higher dimensional space? But we can, in fact, find that by appropriate coding, we can represent by things that look to us at first like pictures of those things in space, and find the rules for for moving these around. And the rules for moving these around may, because they're very simple, end up looking very similar to the kinds of rules that we've been looking at just by thinking about a distinction. I'll point out to you how that works in the case of the topology, and then let's slow down and see what we want to say to finish. But if you're working with knots like this, you can represent them with pictures like this. And what should you be allowed to do with the pictures? Well, I'll do it on a picture. I should be allowed to move it around like that, you see? Because that's a topological motion of the knot. I can just slide it underneath itself, which means that out in the abstractness of it, I should be allowed to have two lines next to one another. Then I could slide one underneath and then back underneath like that. So I should be allowed a rule of transformation of this kind. And if I had something that was in fact unknotted like this, I should be allowed to take this guy down here like that. Oop. What happened? Sorry. I just took this guy and slid him down there like that. I should be allowed to do things like that. I should be allowed, if I had somebody that went like this, I should be allowed to slide it all the way over the other eye down to here. And you see that what we're looking at are properties of the way boundaries cross across one another. You can cross under the boundary and back under, but there's a notion of under and over that's been added in here in order to handle the topology. And here again, it's a crossing pattern. And then another one would be if there was a little loop like that, you should be allowed to remove it. And so this is called number 1, and this is called number 2, and this is called number 3. And it is a long-standing theorem from the 1920s and earlier that that if you want to know whether two knots are equivalent, you draw pictures of them, and if you can get from one picture to another by a series of these moves, then they're equivalent, and otherwise they aren't. And that's the basis of the mathematics of that. Again, the notion of equality being able to move one thing into another. And so you begin to get a view from the bottom of mathematics and also of mathematical physics and many other things about language itself by looking at things this way of starting from the least thing you can, looking at the kind of distinctions that are made and seeing how those distinctions exfoliate into larger structures. If it were physics, then we might go over to Peter's domain and think about the very simple beginnings of the kind of physics that he's describing and what kind of what kind of distinctions are being made. And if you were to look, for example, at the rewrite system, then you see that the rewrite system is talking about the simplest alphabets that you can make and the simplest interactions of alphabets that you can make. And it's very similar to watch how the mathematics grows out of very simple things. And the only mathematics we have ever managed to understand, and I think the only mathematical physics that we've ever managed to understand, has the property that we could explain it in this way of building it out of very simple things. That doesn't mean that the explanation of the world must necessarily come out of how things can be built out of very simple things, but it's what we're capable of. And it's still what we need to continue exploring to find out even more what we're capable of. So this being the end of the hour, I will stop.
Okay, thank you very much for that, Lou. Illuminating and enlightening as always. Now, have we got time for a few questions, short ones? Or do you want one? Ask one, John. John?
Yes, please. Yes. Lou, that was it's wonderful listening to you talk. It's hypnotic, and I thoroughly enjoy it. But a few things have occurred to me in as they always do when you're talking. And one of these is that we're talking about distinctions here, and we're talking about distinctions within distinctions. So if you define a system where a distinction has some value, as you did at some point, that it's equivalent to 1, and a distinction within the distinction is nothing, and therefore is 0, then what one's doing is one's setting up an algebra which is like the algebra of just a single binary digit. It's the subalgebra of that single binary digit. Now, it strikes me that if that distinction has some physical, that it can have one of two things. Either it has no physical effect whatsoever, it has no measurable, the boundary has no effect on any measurable quantity whatsoever, in which case the boundary for all quantities is no boundary. It has no problem crossing that boundary, and the fact that it has crossed that boundary or not is of no consequence, and therefore that boundary does not exist for that physical thing. If that's the case, then the argument follows as you showed it. However, if it does have some measurable quantity, a change of entropy, the fact that something is confined within some volume, or a change of energy, especially some energy change, then a proper way to do this would be to say that your distinction existing in the first binary digit, if you then add a second distinction to that, which goes to 0 in that binary digit, does not conserve that quantity, whatever it is, entropy or energy, let's call it energy, unless there then becomes a distinction in the second binary digit. You see what I mean?
Well, I'm not quite sure. The first question you ask is, should we think of each of these distinctions, or even the lack of distinction, as having a physical effect?
No,
right? Or what would be the physical correlate of what I'm talking about? So if I were talking about drawings on a sheet of paper or markings in a word processor, then even the existence of the blank sheet of the word processor is a physical state. That's a certain physical state. And then the transition to it with a drawing on it is another physical state. So, or in the computer, the binary 0 is an empty register, but that's a physical state.
Yes.
So, the nothing may as well be taken as a relative nothing, right? Not as an absolute nothing, for the sake of representation or physicality.
But if one had a sheet in which one put a mark, so one imposed the mark, and if the system was set up so that one put a mark within that mark, the first mark and the mark which one had drawn then vanished, thus returning one to the state of the blank sheet.
Yeah, that's a transition, right? So
yes.
If we were doing this, we could imagine a little Turing machine. I guess it would be I'm
Yeah,
forgetting the
P1.
name of the guy who did Turing machines with only zeros and ones on the individual squares.
Yeah.
But you could have a Turing machine in which written on a given bit of tape is either a mark or no mark, or a more complicated one where what's written on a bit of tape is a Spencer-Brown expression, and then you could go from one tape state to another tape state by changing it.
Yes. That would then conserve this quantity, which we might call energy or entropy, if one then had a separate piece of paper on which one tallied that set of changes that one had had.
Sure.
And then that would have a connection with physicality, with the physicality of this quantity we're looking at, which could be entropy or energy. So if one
right,
has
so imagining physicality is very interesting, right?
Yes.
What if I imagine the following? What if the mark were an elementary particle?
Yeah.
Well, then this elementary particle has two modes of self-interaction. It can interact with itself to produce itself.
Yeah, which it does.
Or it can be its own antiparticle and go away. Now, the going away then was to some radiated state. A radiated state had to be replacing the unmarked state, or the unmarked state, the non-localized radiated state.
But this is perfect. So if we take a particle which is its own antiparticle, so we take a Wild fermion or something like that, which you've also talked about in the past. So we take something which is its own antiparticle, and then we impose the thing on itself so it vanishes in terms of that state. The state still contains energy, and that energy is then transformed to another state, which is itself a distinction, but it's a distinction somewhere else, or in some other order, if it's to have some physicality and have some effect. So then one has a hierarchy of distinctions, where those distinctions are things that are distinctions at some level, but then that level can transform to another level, which then takes over the essence of whatever it is that is that boundary. Do you see what I mean? This is a nested set of distinctions then, of distinctions that
certainly it is. Yeah. And in this physicality of it, you may want to think about, well, is there enough energy in that vacuum if the vacuum could be equivalent to this great big expression, but it has to have enough energy in order to do that, right?
Yes, it does. It has to transfer to the other physicality. And of course, when you're drawing boundaries, if you draw a boundary which is just a mark, which is an abstract boundary, that's really a different kind of thing to drawing a boundary in 2D, which can have an edge which fits with another boundary. So a distinction which is an area, a two-dimensional.
And those distinctions didn't have to be distinctions in a plane. They could have been like bubbles, and they could have been like bubble surfaces in three-dimensional space, or four spheres in 5 space.
Yes, they could, but then one could also draw them as a set of projections which were distinctions, like the flatland stuff that Sam was talking about earlier. And then
but there is this funny limitation that we think that our signs should be on paper, but I think this is a function of the printing press. Maybe it's Gutenberg's fault.
You're so right. That's right. It's the way we've been doing it since we started scraping bits of skin. Yeah, that's right. It's been two-dimensional all along, hasn't it? Okay. Anyway, fascinating. It's fascinating at what level meaning is given to something. But on the other hand, I think that one also needs to think about whether something has meaning or if it's meaningless. And I think if something is not physical in all dimensions, then in a sense, that is something which is meaningless or has no distinction.
What do we mean when we say it's meaningless? We always mean it's meaningless within a certain context. I try to say something to you, and you're talking about quantum field theory, and you say to me, well, that's meaningless. Yeah, because I don't know the language and I don't say it right.
Yeah, that's right. I don't understand the language.
Got a question from Mike?
Oh, yeah, sorry. Yeah, go for it.
Yes, no, just coming in what you have just been saying, John, to Lewis. Oh, by the way, Lewis, thank you once again for an utterly fascinating, inspiring talk. And there's just so much there. But no, the remark about this all goes to what's sometimes called the symbol grounding problem. Something clearly conceptually very significant happened when we started to write on surfaces, make marks on surfaces. But even prior to that, the content, the essential notion of drawing the distinction that Lou is referring to, I think was already available in purely gestural form. It's actually the more fundamental notion is actually that, if you like, of figure and space in a very, very general abstract sense.
I agree.
Where figure is, I'm not suggesting by figure something drawn on a surface, marks on paper. That's just a specific realization of a much more general notion of figure. But the key thing I want to draw attention to here is that there has to be some kind of source and medium of structuration, which we tend to think of as already spatial, at the very origin of what is sometimes called semiogenesis, the origin of semantic content as such. There's a thesis which some people, I don't myself entirely subscribe to it. I think it's quite closely connected with Russell's idea of neutral monism, and it's been developed by my friend, the Italian philosopher Alberto Baruzzi, the view that every ingredient of cognition is ultimately the transpose of spatial structuration in some sufficiently, if you like, general and possibly very mediated form.
There are creative acts that create a space.
Yes.
So you can reinterpret or interpret the Bible in its statement in the beginning was the word. That word is a space creating word.
Yes, yes. Well, of course, they're the first words of the Gospel of St. John. In the beginning was the Logos, from which, of course, we get the very word logic. Yeah, I mean, I don't want to go straight into theology, but I do think this idea of trying to relate if you like, the very deep and subtle connection between what you might call I would say that the three principal dimensions of the notion of what it is to be a foundation for. What you mean broadly, the kind of logico-semantic dimension, the epistemological dimension, and the ontological dimension, which are related in very subtle and intricate ways, but relating all of these to the question of the, if you like, the question of what lies behind meaning. What is it worth? It is in some fundamental notion of gesture or figure that permits the formation of meaning as such. In other words, relating the origins of mathematics to the question of semiogenesis and semiotics, I think is an utterly fascinating and a very, very deep project.
Agreed.
Yeah. Sorry, I had a bit of an outburst more than a question.
No,
for a
great outburst.
It's a lot of fun.
Any more outbursts from anybody?